Okay, so in this next section, we're going to revisit a couple ideas and concepts that we first introduced when we first started talking about organic compounds, and that's this idea of isomerism and isomers, right? So in chapter 11, we had talked about the ability of organic compounds to exist as structural isomers, and what structural isomers are things that have the same molecular formula but different bonding arrangements or different connectivities of the atoms, meaning that the atoms are going to be combined in a different order, right? So for instance, we can have a molecular formula C2H6O that doesn't really give us a lot of information about the structure, but this molecular formula, those atoms can be arranged in this form, where we have an alcohol, which would be ethanol, which has 2 carbons, 3 into 5 and 1 6 H's and 1 O, right? So that's our molecular formula. Or we can arrange the atoms differently and we end up with an ether, right? With an O between 2 CH3s. We still have our 2 carbons, our 6 H's, and our 1 O, right? So these would be structural isomers. And we talked about that and how that can exist with any or is very common in organic chemistry. We're going to take a look now at a different type of isomerism that can exist in organic compounds and in our carbohydrates, to be a little more specific. So this type of isomerism is known as stereoisomers, and we actually already looked at a couple of these before. So what stereoisomers are, again, they're isomers, meaning that they're going to have the same molecular formula, but they're not structural isomers, meaning that the connectivity is the same between these isomers, but what's different about them is the way that the atoms are arranged in space. And like I said, we had seen a couple examples of these before. So one type of stereoisomers seen before was cis-trans isomers, right? So we saw the difference between those, between a cis and a trans isomer, was just where our groups were relative to the double bond. So now we're going to take a look at some other examples of stereoisomerisms. And specifically, what we're going to be looking at here is this idea of having a mirror image of something. So when we have a mirror image of an organic molecule, and we find that they are non-superimposable, meaning if you place the mirror image, in other words, the reflection image of the molecule onto the original molecule, all of the atoms don't match up. Or do not line up or superimpose on top of one another. All right, so we see that they're non-superimposable mirror images. And we refer to those types of compounds as chiral compounds. Right? You pronounce that chiral, or whatever that says in your textbook. So chiral, that's how you, that ch is a hard K sound. So that's kind of difficult to process. So let's take a look at a couple analogies. And you actually encounter chiral things all the time. Your hand, for instance, both your hands are chiral things. So your right hand, if you place your right hand in front of a mirror, you see the reflection of it, and what the reflection is, it's your left hand. And if you take your left hand and you try to superimpose it or place it directly on top of your right hand, you will see that all the fingers don't line up. Right? In other words, what you have there are two non-superimposable mirror images of each other. So we say that they are chiral compounds, or chiral objects in this case. But we can apply that same reasoning to molecules, right, on a much, much smaller scale. If you do have a mirror image that are identical and that are superimposable, then we say that those molecules are achiral, right? So achiral here meaning not chiral. And that means that the molecules are the same. Okay, so the terminology can be a little confusing, so you want to make sure that you get it straight to begin with. So achiral meaning not chiral, molecules are identical. Chiral means that the mirror image is non-superimposable and those molecules are different molecules. All right, so I mentioned your hands are things that are chiral, right? So for instance, you wouldn't, or you couldn't put your right hand in a left glove, for example, right? Because they're not the same. They won't fit. Similarly, when you put your shoes on, your left shoe goes in your left foot. You don't put your left shoe or your left foot into your right shoe. It doesn't fit. So those are both chiral things. Whereas something that's achiral, right? If you think of having a glass that's symmetrical all the way around, and let's say this was a mirror right here in the middle, right? And this is the mirror image here on the right. So these two glasses here that are mirror images of each other, right? We can actually superimpose them on top of each other and they're the exact same thing. Whereas, so we can superimpose these two images so they are the same. Whereas on the left side here with your gloves, right, just like your hands, right, you cannot superimpose them right on top of each other. So we say that they are chiral objects in this case. So how do we take that and translate it down to the atomic scale when we start looking at molecules? Well, we say that molecules then can be chiral when they have at least one or more chiral carbons in that molecule. So how do we identify a chiral carbon? Well, a chiral carbon is one that has 4 different groups attached to it, right? So what that means then is that the chiral carbon has to have 4 bonds, first of all. And remember, carbon can only form a maximum of 4 bonds. And because those 4 things have to be different, that means that that chiral carbon has to have 4 single bonds attached to it. And those 4 things that it's attached to have to be different. So when you have to identify a chiral carbon, right, we can eliminate carbons from being chiral if a carbon is part of a double bond. So if carbon has a double bond, right, then it cannot be attached to 4 different things. So it cannot be chiral. And also if a carbon has a triple bond attached to it, it also cannot be chiral. So we're looking here, when we start identifying our chiral carbons, right, carbon with 4 single bonds. That's where we can focus our attention in identifying a carbon as being chiral. So if we have a molecule with 1 or more chiral carbons in it, then we're going to end up with non-superimposable mirror images. And the way that we refer to those is we call those mirror images that are non-superimposable, we call those enantiomers. Right, so an enantiomer is a non-superimposable mirror image. So for instance, if I have this molecule here on the left side, okay, so I have a carbon here in the middle, right, and it's attached to a hydrogen, it's attached to a chlorine, an iodine, and a bromine, right? So this carbon here is attached to 4 different things. Right, so that means this carbon is chiral. And the way that we denote a chiral carbon is we use an asterisk. So we can draw a little asterisk here, tells us that that carbon is chiral. And if we look at the mirror image, right, so this is our mirror right here in the middle, right, we're just reflecting all the atoms over on the other side. So the chlorine that was closest to the mirror, that's the chlorine on this side that's closest. The H on top is the H on top here. The bromine that was furthest away is the bromine furthest away. And the iodine at the front is the iodine at the front over here. So if I take the mirror image on the left side and I superimpose it, I just place it on top of the image on the right, we'll see that all of the atoms line up. I'm sorry, all of the atoms don't line up. They don't. Right, so the H's do, the I's do, but the Cl and the Br, right, they don't line up here. So that means these are non-superimposable mirror images. So we're going to call these enantiomers. Right, and there's your chiral carbon right here in the middle. It's attached to 4 different things. And if we compare that to this structure here on the bottom, all right, so we have this molecule here on the left side, and there's our mirror, so we're going to reflect it. So this bromine here is closest to the mirror, that one's closest to the mirror. The hydrogen on top is the hydrogen on top, the chlorine furthest away becomes a chlorine furthest away, and then the bromine at the front and the bromine at the front. So if we take this here and we put it over the other one and we rotate it 90 degrees, what we actually see is that all of the atoms superimpose. So these 2 molecules then are actually the same. They are identical. So these are not isomers, structural or otherwise. They're the exact same thing. So we can confirm that by looking at our carbon here, right? Is that carbon attached to 4 different things? Well, let's see. There's an H, there's a Cl, there's a Br. Those are 3 different things, but then there's another Br. So it's only attached to 3 different things, right? These 2 here, both bromines, are the same. So this carbon then is achiral, so that means we don't have the possibility of enantiomers. Okay, so let's take a look at a couple of these here to see which of these compounds are chiral, and specifically identifying which carbons are chiral or not. All right, so let's take a look here at the structure on the left side, A, and we'll focus in on each of the carbons and kind of walk you through how to identify chiral or achiral. All right, so let's take a look at this carbon. Is that carbon chiral or achiral? Well, what is it attached to? Is it attached to 4 different things? And the answer is no, it's actually attached to 3 H's, which are the same, right? So this carbon here is not chiral. And then this C here is in the exact same boat, right? It's also attached to 3 H's that are the same. So that's not chiral. This carbon here is attached to 2 H's that are the same, right? So that carbon is also not going to be chiral. Whereas now this carbon here in the middle, all right, let's see what it is attached to. It is attached to a chlorine. It is attached to an H. It is attached to a methyl group, and it's also attached to an ethyl group down here at the bottom, right? So this is attached to 4 different groups. So that carbon is chiral. So we'll use a little asterisk here, and because my compound now contains at least 1 chiral carbon, then we'll say yes, this is going to be a chiral compound. All right, this one here in the middle, B, right? This carbon is not chiral because it's attached to 3 H's. This carbon here, right? It's also attached to 2 H's, so it's not attached to 4 different things. This is also not chiral. So this compound does not contain any chiral carbons, so it's going to be achiral. Right, the one on the right here, C, this carbon here is attached to 3 H's, so this carbon is not chiral. But this one here in the middle, there's a chlorine, there's an H, there's a Br, and there's a methyl group, right? So that one is chiral. So this then is going to be a chiral compound because it contains at least 1 chiral carbon. Okay, and let's take a look at another example of where we can identify carbons as being chiral or not. So let's take a look at this structure. We're going to try to identify any chiral carbons in this. All right, so the first thing we can do is, if we can't identify them immediately, first of all, eliminate carbons that we know cannot be chiral. Right, so we said that, if a carbon has a double bond or a triple bond attached to it, it cannot be chiral. So right away, we know that in benzene, right, all the carbons in benzene are achiral because they all have at least 1 double bond attached to them, right? So we can eliminate all of these from being chiral. Which leaves us then with just 3 other options, all right? So what's over here? Well, at the end of the line, remember there's a carbon, and then we don't draw the H's in, but in order to make carbon happy, that has to be 3 H's. So that's a methyl group at the end. So that also cannot be chiral because it's not connected to 4 different things. What about this carbon here? Right, so this carbon right now is attached to a methyl group on the right side, and it's attached to all this stuff here on the left, but what else is it attached to? The remaining 2 bonds are to H's, right? So that carbon also is not attached to 4 different things. So that one also cannot be chiral, which leaves us then with this one here. So let's take a closer look at that carbon, and we'll just draw out all the bonds. So right now, that carbon is attached to a chlorine on one bond. It's attached to a benzene on the left side. It's attached to all of this stuff here on the right, which is an ethyl group. Those are 3 bonds. Well, what's the 4th bond to? Even though it's not shown, that 4th bond is to an H. Right, you have to understand that that H is there. So this carbon here is attached to 4 different groups. That is going to be our chiral carbon. We can identify it with an asterisk. All right, so that's how you can go through systematically and identify which carbon is chiral in a compound.